In this video, we're going to look at the classification model that is called naive Bayes, which apparently I have forgotten to put on this particular slide. So lovely. Right here in the middle between support vector machines and these last three methods is the naive Bayes, which I don't know, forgot to write down. All right, so when do you use naive Bayes? Well, naive Bayes, like the k-nearest neighbors, works if you have missing information. And where we're going to look at naive Bayes is that unlike the other methods, it is the only one that works when you have nominal predictor variables. So if you have categories, then you can use categories to predict other categories. So our labels, of course, are categories, but we can use variables that are categorical nominal data to predict that. That also means that our naive Bayes is going to be used for natural language processing. So we're going to use it for text classification and sentiment analysis. So naive Bayes we're using when we're analyzing text. It does not require a large training data set. And as I said, the key here is that it can be used with nominal predictor variables. It can also be used with ordinal, interval, or ratio predictor data. It doesn't have to just be nominal. But that distinction makes it popular with the text classifications. It can be used to identify binary labels or multiple labels. So yes, no, right, is the binary. So it is or isn't something, as well as the multiple labels, which group it belongs to. So let's take a look at how naive Bayes works. Just a reminder, we are working through drstephpowers.github.io/BIA. We're working through the workbook called Classification. Click on that. You'll find, when you go in, not only the Python workbook, which you can open in Colab, log into your Google Drive, save a copy for you to work on. But the other thing you'll need is you'll need these data sets. And as I said, the naive Bayes allows us to work with nominal data, like text labels. And so we'll need this attribute data set from Usman and Ahmed, the UCI machine learning repository. So make sure that you grab that data set in addition to the ones we've been working through in our previous videos. All right, let's dive in here. So to do the naive Bayes, let's start with nominal, ordinal, and ratio predictors. Let's have a mix of variables we're going to use to predict. So in order to do this, we are going to use skylearn.naive_Bayes and import the Gaussian naive Bayes. We're going to have it separate out our data set into the training and testing samples. So we're going to use train_test_split from model selection rather than specifying for ourselves what's in the testing data. And if we are going to do a binary label, then we can use precision score, recall score, and confusion matrix. If we are going to do multiple labels, then all we get is the accuracy score. So we make sure we have our packages. Okay. And what we're going to be doing is we are going to be looking at this attribute data set. So make sure you have it loaded. We call it DRESS for short. And then I gotta go back to where I had it. Let's see. Naive Bayes. That's the one after. All right. So just to take a look at the data set here, what we have is we have different dress IDs. They are labeled for different styles, different price ranges, low, medium, high, or sorry, average, high. They have ratings in terms of how much people like them, the size, the season, neckline, sleeve length. That's not spelled correctly, but it should be waistline. Material that it's made of, fabric type, decorations, pattern type. And then lastly, they have a label here as to whether or not that particular dress was recommended. So if we're trying to then predict what particular outfit is going to be recommended, we can use our data set here with our labeled data that has 1 for recommended and 0 for not recommended. So binary, okay? Which means we can use our precision, our recall, and our confusion matrix to create our data set. Now, let's say that we're going to try to predict that's recommended, and we want to take a nominal data set or nominal variable like style. Okay, so in order to do this, we're going to have to change this column called style, and we're going to need it to be a category. So we're going to do dress style as type category. And then we see the same code we saw back when we made the pie charts and the donuts. We need it to list the different categories. So that's what this set of code here says, is that we're going to make dress style type a category type, and then we want it to then find the categories and list them for us. So when we do that here, we see that there's some different categories: brief, casual, flair, novelty, sexy, bohemian, cute, fashion, party, sexy, vintage, work. Okay. All right. Now, what we can do here is we can then create a loop that is going to loop through the length of this list here. And it is going to then replace the category with, what did I do here? Let's run this. Let's see what this is here. Code, and then show me dress style. Not curly brackets, hard brackets there. Show me this. Okay, so here we can code this, right? So we can say for the length of this list, what we're going to do is we're going to take our data and we're going to code this. We're going to call this 1, 2, 3, 4, 5, 6, 7. So we're going through and we're doing I+1, and that allows for this label. So brief will be 1, casual will be 2, flair will be 3, novelty will be 4, and so on. So then when we look at our data set, now we look at the dress style, we have a category type, and then we have 13 different labels. Okay. Now when it comes to dress price, again, we can look at changing it to category and identify the categories. Notice that in this case with the dress price, it's not just simple. They have kind of conflicting categories, right? So we have a high that's capitalized, we have a high that's lowercase, we have a low that's capitalized, a low that's lowercase, and something called very high. So what we're going to do is we're going to take this data, we're going to clean it up a bit, and we're going to call low 1 and lowercase low 1, and we're going to call medium and average both 2, and high, capitalized and lowercase 3, and very high we're going to call 4. So we're going to use replace to replace these different categories so that there's consistent formatting, so that we don't have these things that really do mean the same thing that it can't differentiate because one's capitalized, one is not. So we're doing a little bit of cleanup of this data set initially. We're coding the style. We are going to code the price. So price is going to be ordinal, style is going to be nominal, and then let's do seasons. So we have it take the seasons, identify the categories, and then make a list for us of the categories. And notice that there's some typos, right? Autumn is spelled 2 different ways. Spring is capitalized and not capitalized. Summer is capitalized and not capitalized. So we're going to need to clean this up as well. Once we replace the typos, make sure everything that's autumn is spelled the same and spring is all the same capitalization or lowercase. So in this case, we're changing autumn with an O to autumn with a U, and lowercase spring to capital spring, lowercase summer to capital summer, and lowercase winter to capital winter. So we're creating that standardized formatting. Then what we can do is we can check that it all got covered by doing our same process where we label the category and then we tell it to find the different categories. That's what this code is here. So we can now see we just have 4 seasons, autumn, spring, summer, not the giant list that we had before. And then we'll need to code it, because in order to do our naive Bayes classifier, we need coded data. So we can't use it in its text form. We'll need to code it here. So we're going to create a loop that's going to go through the length of our styles. So through these 4 here. And then it's going to go through the variable season in our data set. And it's going to replace whatever's listed under season with a 1 for autumn, 2 for spring, 3 for summer, 4 for winter, and the change is happening in place. So now when we look at the actual data set, you can see that the price now is ordinal, 1, 2, 3, 4. Our style is nominal, coded 1 through 13, and our seasons are coded 1 through 4. So now we can build our naive Bayes classifier. So what we're going to do is we're going to create a subset. We're going to create, we're going to create a new table called dress 2, and it is from dress. It is just style, season, price, and recommendation. And if we were going to manipulate this further, we would do a copy of this as opposed to just the subset that's renamed. But we aren't actually going to do anything with it but load it into our classification model. So it doesn't really need to be that copy that we've used before. So we're going to create this new table called dress 2. And we're also going to drop the NAs. So here we're going to remove them. Now, one of the benefits of naive Bayes is that you don't have to. You could leave it in its original form. It does allow for missing information, whereas other models don't. But we still have a lot of data here. We have 500 data points, even if we drop the missing ones. So you can choose with naive Bayes and with K nearest neighbors, they do allow for that missing information. But you can choose here if you're going to get rid of that particular rows or not. Then what we're going to do is we're going to have it choose what data goes into the train, what data goes into the test. We want to pull style, season, and price. Those variables are going to be the ones we're going to use to predict whether or not it is a recommended outfit. And so then we're going to have comma dress 2 recommendation. That's going to be the labels. We're going to do our 80-20 rule. So we're going to have a test size of 20%. And again, we're going to stratify by the recommendation to make sure that both the training data and the testing data include both recommended outfits and non-recommended outfits. To do the naive Bayes, the model that you're going to call is called Gaussian naive Bayes, and then parentheses. Make sure that you have the proper capitalization. It matters, so capitalize G, N, and B. You need to give it a name, so we'll just call it GNB. And then you're going to fit GNB on your training data. So X training data, Y training data. It's created our model. Now we're going to use our model to predict. So we're going to apply it to the testing data. So let's have it predict the labels for that X data. And so here's the outputted predicted Ys. Now to see how accurate this model is, we can use our accuracy underscore score, Y test, Y predict. And this particular model here has a 61% accuracy. Now notice here that we did not specify the random state. And so if I ran this again, so I'll just show you here, this one has a 61% accuracy. If I run this again, and go through it again, it has randomly generated which data goes into the test and which goes into the train, which means it's going to predict different numbers. And the accuracy is going to change. That one was 61, but you might get a slightly different number, 59, 56, depending on what ended up in the testing data and the training data. So you can put here a random state equals, like we saw previously, if when you rerun this, you want to get the exact same results. I haven't put one here. When you run it on your own code, you're going to get slightly different prediction values. You're going to get slightly different accuracy because it's going to randomly put different rows into the test and the train. So we're going to get different information here. That's okay. And so when we create then our confusion matrix, you're going to end up probably with slightly different numbers because we're not using the same random starting point or random state. Either way, you want to see what we find here. So we're going to display our confusion matrix. And we've talked in our previous videos about this code here. So we're just using that same code and same display. And so what we find here in this particular run is that we have that it predicted here that it should be recommended. For 6 of them, it predicted it should be recommended, and it was recommended. Okay. And then we have 55 where it predicted it should not recommend it, and it didn't recommend it. But what we see here on these 2 other angles here is that we have ones where we predicted it should be recommended, but it wasn't. So these are the false positives. So we have 3 false positives. And then we have ones where we have 36 where it did not recommend, but we should have recommended. So we have 36 false negatives, which is going to impact then as we look at our precision and our recall. So notice here this recall score is much lower than the precision at 14%. And that's because this particular model is having an issue with false negatives. So it has a high number of false negatives, even though it has a small number of false positives. So we have to ask ourselves, is a false negative a big problem for what we're trying to do? So in this case, it's not being recommended, even though it should be recommended. Now, that was with our mixture, right? We had data there. We were using, let's go back. What were we using? We used style, season, and price to come up with the recommendation. And we saw that it had an accuracy of 61%. So the question is can we come up with a better model that has a higher recall score, so has less false negatives? So perhaps that's more variables to help us figure out the recommendation. Maybe those 3 variables alone aren't enough. One of the challenges is that if your variables are mostly nominal, there's less variability in them, right? So you have all these different data points, your huge sample size of 500 or 10,000, but if there's really not a lot of variability in those predictor variables because they're all nominal, they fall in one of these 3 categories or one of these 4 categories, it might be hard to suss out to get those nuances of the different classes. So it is the ordinal and then even better the interval and ratio data that's going to have more variability that's going to create the more robust models. So something to consider as you're building these, but of course you're going to be limited in terms of what variables, what data is relevant, what have you collected. So let's look at this particular example here. This particular example has the nominal and ordinal. Let's just figure out what's the difference between that was rating, season, and price. Okay. So this previous one was style, season, and price. Maybe style is not that helpful in whether it's recommended. So we could sub out the style and try rating instead. Okay, so let's see if rating gives us a better recommendation. And let's just go back and look at, actually, let's just pull it here. So we're going to pull from the dress, the rating, season, price, and recommendations. And here again, we're dropping the NA, the empty rows, but you don't have to with these. So let's just show me this. All right, so here we have a bit more information. This rating, it is rating it from probably 1 to 5 here. And so let's do the season, let's do the price, but let's see if we can get more information based on the customer rating. All right, so we're going to do the same thing. We're going to do our train test. We're going to have it split the data up. So we're going to use rating, season, and price in order to predict whether something is recommended We're using our 80-20 rule. We're going to stratify by the recommendations to make sure that both the test and the train contain those that are recommended and not recommended in both. We're going to call our naive Bayes model. We're going to fit our model, X train, Y train, and then we're going to predict the values. And let's then calculate the accuracy with our new model here. So our accuracy here is at 62%. And we can create that confusion matrix just like we have before. Again, we're not using a random state, so we might get slightly different things than you get when you run the code. So your numbers may not be exactly the same depending on what ended up in the test and the train. So when we look at this one here, what we can see is that it still has the issue of the high false negatives, right? And so it was able to say 55 correctly should not be recommended, 7 correctly should be recommended, but we have 35 here where it predicted it should not recommend them, and it did. So our precision score here, we run this, we get 70%, and our recall score is still low, sitting at 17%. Now, we were talking about in the previous video how there's this trade-off between precision and recall. And so we can create what is called a precision recall display. To create a precision recall display, we take sklearn.metrics, we import precision recall display, okay. And then if you have your X test and your Y test, and you have your fitted model, so remember we called this fitted model GNB, so go up a little bit right here. So GNB was the model that was fit. Once you have that, you can then do this precision recall display dot from estimator GNB, that's the model we fit, X test, Y test, and we get this precision recall display. Okay. In our precision recall display, what we're looking at is this trade-off between precision and recall. So if we adjust the classification boundaries, so remember we're looking at, again, recommend, not recommend. So similar to the ROC curve, we're looking at what if we changed in the algorithm where that cutoff was in terms of what pushed it to recommend or not recommend. This is showing similar information here. And so what we see here is that for the model that includes rating, the average precision here is 58%. And that if we had a higher level, so if we had higher precision, then what would happen is it would lower the recall. So we're trying to find this sweet spot in terms of the cutoff in the algorithm. And we can see here that at our average precision of 58, about here, we're getting a recall of about 30. That's kind of the optimal combination given the variables that we've given it. So if we run this a bunch more times, and what we're going to get is an average precision about 58, and corresponding with that is an average recall that's about 25. So in this scenario, right, we got that 16% recall, and so we could slightly do better if we ran this another time, but that's kind of showing you what this gives you. And so we would think about maybe we need some different variables, provide us a bit more information, better variables that are related to the recommendation. Again, maybe we can find some ratio or interval data that has more detail than we get with, say, with nominal or ordinal. That could help with that and improve the model. But this is kind of showing you that if the model itself adjusted that boundary decision to make it more in terms of precision, you lose recall. And if it was to focus on recall, you would lose precision. And so coming back to this here, what we're seeing here right now is a bunch of the false negatives if it changed that cutoff, we would move towards more false positives with that boundary that you can't optimize both within the same algorithm with the same data set. And so we got to look at sample size, we got to look at the variables we're using in order to improve the accuracy of our model. So this precision recall graph, you can use this for any of the binary classifications. We're applying it here with the naive Bayes, but you could come up with the same graph and use it with our generalized linear model or support vector machines. So just to add a bit different knowledge each video, not just on the classification model, which can get a bit repetitive because it's the same: call the model, fit the model, and then predict and so on. Test and train, we can either specify by withholding ourselves what the testing data is, or more commonly we'll have it generate the data for us. So lots of different options as you're building your classification model. As we continue looking at the naive Bayes can be used not just for the binary labels, but it can be used for multiple labels. So we could, for example, use the naive Bayes. Let's go back to kind of an old example we were using before, which is, this is data frame 3. This is the customer relationship management database. We had withheld for different data points to look at, could we predict, and in this case, we're going to predict the salesperson. Can we predict the salesperson using their listening percentage and their talking speed? If you were going to do this with the naive Bayes, we need to import naive Bayes. We need to import accuracy. Remember, precision, recall, none of that works when you have multiple labels. So all we have is accuracy here. We have our training data was the data set. So data frame 3, questions 7 and 8. These were ratio data. We convert it to NumPy. Notice here, when we're not using the test train package, we have to do this conversion to NumPy. When you are using the test train, it does it automatically for you. And then the difference between naive Bayes and, say, K nearest neighbors, and SVM is that naive Bayes is not a distance-based approach. So you don't have to standardize the data for the interval ratio with naive Bayes. So with K nearest neighbors and SVM, you had to use that standard scalar. With naive Bayes, you don't have to do that because it's not a distance-based classification model. We have our X test. If you go back to previous videos, this is the same testing data we used early on. So let's load that in. All right, so what we need to do is we need to do GNB equals, and then we're doing our Gaussian NB, open. Let's build that model. Let's fit that model. Then let's predict. We are going to predict using our testing data here. And then we have our predictions. We have the actual data we withheld. This should be the same as it was before. And so you can see that here we have in this particular model an accuracy of 50%, which was similar to what we got with the other models. So it's quite possible the 4 we withheld, this Smith one and this Mensa one, just really aren't quite consistent with the rest of the data set. And so we can't seem to get past that 50% accuracy. So that's why doing the test train and having it randomly pull might be better in terms of coming up with how good the algorithm is, rather than us specifying specifically that these particular data points are the ones we're going to use for testing, because what if those testing ones are really not consistent with everything else? So you can see that we can use the naive Bayes when we have data that has multiple labels, when we have integer predictors. We can also use it when we have binary predictors. We can also use it when we have nominal and ordinal, binary labels, and when we have nominal and ordinal predictors.